This is example 10-7, shower flow. So we are looking at a shower where the water is coming into the pipe at A and then flowing upwards through this T right here, past a valve, around two elbows, and then through this shower head. And we are given what the pressure is down here, and we are what the velocity is down here, and we're asked to find what the pressure is. So to do that, of course, we will need the energy equation. So it's our common start. Energy equation. What do we get? We go from A to C. So we can say PA over gamma VA squared over 2 times G plus ZA plus H pump is equal to PC, not PB, PC over gamma plus VC squared over 2G plus ZC plus H turbine plus HL. Now in our case, of course, we'll have losses, both major losses from the flow along the pipe and then minor losses for the elbows, the T, the valve, and the shower head. But before we get to those, let's do our regular steps. So let's start with our datum. In our case, we'll put the datum at point A. Datum at point A. What does that mean? That, of course, means that ZA is equal to 0. And ZC is then 1 meter plus 2 meters. That's 3 meters. Minus 0.15, so that would be 2.85 meters. What else do we know? Well, we know that point C is in contact with the atmosphere, so our pressure is going to be 0 there. Point C in contact with atmosphere, so PC is equal to 0. We're given PA somewhere in here. No, we're given VA, not PA. So PA is what we're trying to find. PA, PC, VA we're given. That means we need to find VC. All right, VC. Well, it's a continuity equation. Right? We have water coming in at A, going out at C. So we can say VA times AA is equal to VB times AB. That means if we solve this for VB, then we'd have AA over AB times VA. So that means our cross section at A is a circle, so pi over 4 times dA squared. Now, in the shower head, it's also circles, but it's 100 circles with 1.5 millimeters. So we can say 100 times pi over 4 times d, let's call it C squared. It's not really the overall diameter at C, but we'll know what we mean. Times VA. Of course, that means that our pi over 4's cancel out. So we'd have dA over dC. That is squared. Now, careful you don't forget the 100, so let's divide the VA by 100. All right, so let's plug that into our calculator. So we have dA is 20 millimeters. 20 millimeters. The holes were 1.5 millimeters. Well, we don't have to change the units because they cancel out. And then the velocity was 2 meters per second right there at the top. Times 2 meters per second divided by 100 for the 100 holes. That gives me 3.55556 meters per second. All right, so now I have the velocity. Here we have the Z's, H pump, H turbine. We don't have any, so that's easy. No turbine or pump means H turbine is equal to H pump is equal to 0. With that, we're left with HL. All right, so we'll have minor and major losses. Let's start with the major losses. Major loss along pipe. We know that is HL, let's call it MA for major, is equal to F times L over D times V squared over 2G. All right. Now, do we know what the, we're given what F is. All right, good. That makes it easy. We don't have to go into the Moody diagram. We can just plug in numbers right away. But let's put an A in here just to make this very clear. So we were given that F is 0.016. Now what is the length of our flow? 1 meters, 2 meters, 2.8 meters, 3.8, and then back down 15, so 3.95 meters. Oops, there we are. Times 3.95 meters divided by the diameter, that was 20 millimeters, 0.02 meters. Our VA was 2 meters per second. That's the flow coming in, squared, over 2 times 981 meters per second squared. That gives me 0.64424 meters. That'd be our major loss. Then we can also find our minor loss, right? So what do we say? We said we have a minor loss. And we had that, let's see, we have 3 elbows. 1, 2, 3 elbows. So we can say minor loss at 3 elbows. They're all 90-degree elbows. What else? We have our gate valve here. And we have a T right there. So we can say gate valve. And T, so now for this one, for the T, right, we get different ones depending if it's branching off or if it's going through, right? T would be something like this, right? That makes a difference if it flows like this or flows like that. For us, it flows straight through, so we'll say that is along. And what else? We also have the shower head on top. And shower head. All right, so that means that our HL MI for a minor is equal to, now we have KL for the gate valve. We have 3 times KL for the elbow. We have KL for the T. Now the tricky thing here is that the velocity in our shower head is different, so we'll do that separately. So we'll say that is all good here. So that we then times VA squared over 2G, and then we'll add the KL, that's called shower head, times VC squared over 2G. And all of these things we can look up, and we can do the calculations. All right, so we can look that up. For our gate valve, we know it's 0.1. For our elbows, it's 0.9. For our T, if we're going straight through, is 0.4. VA was 2 meters per second. And then divided by 2 times 981 meters per second squared. Now for the shower head, I think we're given that somewhere. Yeah, 0.45. So that would be 0.45. Now the velocity is the one that we calculated, so 3.55556 meters per second divided by 2 times 981 meters per second squared, and that gives me a total of 0.960698 meters. All right, let's go back to our energy equation. We are looking for PA. We have PC, we have VA, we have VC, we have the elevations, we have all the H's, so we're good, so we're ready to go. So let's write our energy equation. So we have PA, that's what we're looking for. We said that we know what VA is, so we have VA squared over 2G. We said that our elevation is 0 and our pump is 0 because we don't have one. At C, we said that the pressure was 0 because of the atmosphere. VC squared over 2G, we calculated VC. We know what ZC is. We know we have no turbine, so then we have HL major and HL minor. And so those are all values that we can figure out. So let's solve all this for PA. Right, so we'd have PA over gamma is then VC squared over 2G. We can bring the VA over, minus VA squared over 2G, and then plus ZC plus HL major plus HL minor. All right, so if we want to get PA, right, so we multiply by gamma. That'd be gamma times VC squared minus VA squared. Right, we can just pull those together over G plus gamma times all of those lengths. ZC HL major plus HL minor. All right, so one more little thing to do, and then we'll plug in numbers, right? We can know, of course, gamma over G is just rho. So we can say that's rho over 2 times VC squared minus VA squared. We're not given gamma, so let's write this as rho times G. ZC plus HL, not LT, HL major plus HL minor. And with that, I think we're ready to plug in some numbers. So we'd have to go and look up our density for water at 40 degrees C. And that turns out to be 992.3 kilograms per cubic meters divided by 2. Then we have, let's make this a square bracket. So we have 3.55556 meters per second squared minus 2 meters per second squared plus 992.3 kilogram per cubic meters times 9.81 meters per second squared, and then ZC was 2.85 meters, and then we have the major loss 0.64424 meters plus 0.960698 meters, and all that together gives me 47,654.1 pascals. Which of course is 47.6 kilopascals. Right, that will be our solution. Now, where's our PA? Somewhere up there. And one thing to once again point out, that just because we call them major and minor losses doesn't mean that one is bigger than the other. Right? In this case, our minor losses are bigger than our major losses. All right. So this now, well, quick recap, right? So we have this shower. We used the energy equation and then went through all the terms with the losses to figure out that the pressure down here was 47.66 kilopascals.